Okay, thank you for visiting this virtual introduction to research in the Peters Group. The group itself has 9 members currently, 8 PhD students and 1 postdoc. The main areas of work that we can be divided into 3. There's a methods and theory component, there's a catalysis component, and there's a nucleation and growth component. And I would say that it's a unusual breadth of topics for a research group. I think that makes it exciting because you can learn about so many different project areas. My own background, I came from research groups that were somewhat like this. Arup Chakraborty had, people studying polymers, people studying immunology, and people studying catalysis all in one group. And those seemed like pretty disparate things, but he managed to apply statistical mechanics to them in a really wonderful and satisfying way. And, I try and do the same thing with applying this framework of rare events. This is the sort of overarching theme of the group. We use this rare events framework for formulating reaction rate theories, a systematic way to exploit time and length scales so that we can predict rates, formulate multi-scale models, and interpret experiments and simulation results in a really rigorous way. Our group has contributed numerous state-of-the-art methods in this area. We have made the leading method for identifying reaction coordinates, which is important because it's the core component of basically all rate theories, the starting point for formulating theoretical models and building free energy relationships. All that stuff really comes out of knowing what the reaction coordinate is. We've also contributed a lot of methods to compute free energies, the driving forces for chemical reactions. So these include, for example, methods to compute chemical potentials of solids, polymorphs, and molecules in solution, ways to compute interfacial free energies. For example, I'm showing down here the first calculation of the Tolman length for water. What we've been interested in lately is computing solid-solid phase diagrams with multiple components. And that's an entirely new and difficult thing to do with atomistic simulation. And I think if we can do it, it opens the door to lots of other things that we're interested in the arena of nucleation and solid-solid phase transformations. We wrote the leading textbook on reaction rate theory and rare events. I think the main theme of the book is that when you think about multi-scale modeling, usually people are marching up the diagonal somehow. You see this diagram everywhere you go. There is an alternative and really powerful way of doing this that is the rare events approach, and that's to exploit asymptotically exact ways to take your atomistic MD results or your ab initio calculations, compute the rate constants, formulate a rate law, and then plug that rate law into continuum balance equations. And you can, what I think makes this so powerful is that these 2 steps are asymptotically exact. And so instead of losing a little bit of accuracy at every step along the diagonal, you can use rare events methods. And assuming you start out with an accurate model of what's happening down here at the all-atom quantum mechanical or molecular force field level, you really end up with predictions at that top scale. Just as accurate as that model. Powerful statement, and yet it's absolutely true. And that book is used in quite a few of the graduate courses in other programs that you might be looking at. So you can come to Illinois and learn from the author himself. All right, so we also do we do a lot of method comparisons and critiques of things in the literature. The next area that I want to talk about is our catalysis efforts. There's quite a bit of different scales of phenomena listed here. You see down in the lower left, we're modeling reactors and pellets and boundary layers and transport in and out of pores. So we do a lot of that stuff, and that ends up being really important in making the connection between the ab initio calculations, that's quantum mechanics, statistical mechanics, and molecular simulation tools. If you want to connect those results to the things that your collaborators are actually measuring, it often requires that you go through and think very carefully about what happens between those active sites and the bulk that's being sampled and put through the chromatography units and stuff. So there are really 2 main areas that I want to talk about here, 2 active projects that are consuming a lot of my attention, and really, I think at this point are probably about half the funding in the group. So one of those is the polymer upcycling area. This is really exciting. It's a enormous problem. Just to put it in perspective, there is nearly 10 to the 10 tons of polymer materials and plastics have been made since the beginning of the industry back at the end of World War II. Most of that is being discarded or put into landfills, and it ends up sometimes floating around in big trash flotillas on the ocean. And if you want to get an idea of just how much trash either buried in the dirt or floating around, it's approximately 1 ton per human being. And so this is sort of our legacy as humans, that we inherit this this waste, and I think eventually, we need to put that back in the carbon cycle and clean up the messes. Of course, there's a lot of different plastics being made, but the lion's share is polyethylene. I'm part of an EFRC. I'm the theory lead on the EFRC, so that's a lot of collaborations with a lot of experimental groups that is really working to solve the real problem here, and working on different methods and new catalysts to solve the polyethylene problem. We have some chemistries inspired by Damien Guéronnet, colleague here at Illinois, that we're working on. We have a chemistry inspired by nature. This is sort of a synthetic version of a catalyst inspired by cellulase, the one that nature uses to recycle cellulose polymers. And then we have nanoparticles and porous support. They're really exciting research areas. The bottom panel here is a publication in Science from last year. The top one is a publication in Nature, Catalysis. They're viewed as quite important research topics, and I think the area has a tremendous future in research. Okay, the other area that we work in is thinking about catalysts in amorphous supports and just in general amorphous catalysts. So these are sort of orthogonal, mutually exclusive with most of the theoretical research that's being done in the catalysis field, but they are extremely important. So most people in catalysis are working on zeolites or metals or metal oxides, things that have present crystalline surfaces. But these amorphous materials, every site is different, and when you do active site counting experiments, you often find that only like 1% of the sites are active, and yet these things are really important industrially. So if you look at the entire panoply of olefin transformations, there's polymerization, there's epoxidation, there's metathesis. A lot of those catalysts are made this way. They're single metal atoms or a single metal atom precursor grafted to an amorphous support, and now all of those metals are sitting in a unique environment. And so it kind of deviates from the textbook description of catalysis, and yet industry is really using these. So we dove in and decided, we develop computational methods, so this is a perfect area for us, and we should try to figure out how to do this. What we are doing is using a combination of importance sampling, which is a technique from statistical mechanics. We're using ab initio calculations, which of course involve quantum mechanics, and we're using machine learning tools. And these things are all coming together so that we can learn the nature of the distribution that we don't a priori know, and particularly learn the nature of the tail. And to give you an idea how this is different from typical machine learning calculations and how it's different from typical catalysis applications, and this is a distribution of activation energies on the different sites that are present. The only ones that are going to actually do anything are these ones out here on the left hand into the tail. And so what ends up happening is that the site averaged kinetics are very different from the kinetics of an average site. And so we're wanting to quantify that so that we can go and figure out what are the characteristics of that 1% of sites that are actually doing all the catalysis, and could we make a catalyst that had more of them or was entirely like them. Then the last area that I want to talk about is our work on nucleation and growth. So there were lots of powerful nucleation methods for studying nucleation in single component systems, but there was really nothing for computing rates in multi-component systems. And we developed this seeding method, which was the first one to do that, and is still, I think, the leading way to compute nucleation rates in these systems. Now is used in lots of applications, even has percolated over to people using it for single component systems. In addition to the work on nucleation, we also study a lot of crystal growth problems. We did the first calculation of spiral growth rates, starting from atomistic simulations and going all the way to the observed growth laws with no adjustable parameters. So that was kind of exciting. This is just for sodium chloride, but I think it opens the door to lots of interesting applications for the future. Eli Lilly has been excited about that and funded our work over the past few years to look at trying to do this where active pharmaceutical ingredients. And so we're doing a lot of work with them to compute delta Gs for different polymorphs, nucleation rates, and growth rates for different polymorphs. Currently, our main areas of interest here in nucleation and growth are looking at nanoparticle nucleation and growth. That's, for example, applications where you want to make quantum dots or you want to make metal nanoparticles for catalysts. what are the kinetics? How do you control their sizes? That we're making progress on that. So there's another area is the API nucleation. I already talked about that a little bit. For example, the work that we've done with Lilly. And the last area that I want to mention is this new MURI Center, Multi-University Research Initiative. We are the theory and modeling lead on that. And that's about antifreeze protein. Organisms use these antifreeze proteins to survive harsh winter conditions well below freezing. They can basically arrest the growth of ice. So this is, again, a phenomena that bridges a lot of different scales. I will go ahead and conclude there. Hopefully see some of you guys at the posters.